Welcome. In this video, we will discuss thermal management. Reasons for using thermal management include improving reliability of electronic devices and systems and preventing their premature failure. Also, electronic device performance can be improved. Microcontrollers, as an example, will throttle their performance due to heat. And if thermal management is implemented correctly, it can be a large cost saver when compared to late thermal management design, meaning after the PCB is created, which can significantly increase the cost of the thermal solution. One approach for thermal management is the use of cold plates. Cold plates provide localized cooling of electronics by transferring heat from a hot device to a liquid that flows to a remote heat exchanger and dissipates either into the surrounding air or to another liquid in a secondary cooling system. At their basic level, cold plates are metal blocks that have inlets, outlets, and internal tubing to allow liquid coolant to flow through. Heat pipes are a transport mechanism used to move heat from the heat source to an area where the heat can be dissipated. Heat pipes do not actually dissipate the heat, rather they are integrated into various different types of heat sink solutions. The heat pipe is a copper tube with an internal wick structure that is sealed on both ends with a small amount of water inside. As heat is applied to the heat pipe, the water will boil and turn to gas, which will move to the coldest section of the heat pipe, where it condenses back to a liquid. The performance of a heat pipe is a function of its length, diameter, wick structure, and overall shape. The larger the diameter, the more heat that can be transported, but the longer the length, the less capable the pipe. Heat pipes can be bent and or flattened as needed, but such modifications reduce the amount of heat that can be transported. Convection air cooling and forced air cooling are perhaps more common types of thermal management approaches. Convection air cooling is where heat is transferred from the hot device by the flow of the air surrounding the object. Forced air cooling makes use of fans. TIM, or thermal interface material, is a material that is inserted between two parts in order to reduce thermal resistance between these two components. Lastly, thermal electronics or thermal electronic modules can be used for localized spot cooling. When a DC current is applied to these solid-state devices, electrons pass between two semiconductor material types, which cause the temperature of one side of the thermal electric module to decrease and heat is absorbed. If the direct current is applied in the other direction, the electron movement and heat pumping is also reversed. For more information on this topic, check out the Marlow product training module. For today's demonstration, I'll be showing various thermal management options. This is a mini-channel cold plate from Advanced Thermal Solutions. As you can see, it simply looks like a metal block that has an inlet and an outlet to let current flow through it. It also comes with two of these kits which are used for attaching the external tubing. This is a thermal pad from Laird Technology. At temperatures above its transition temperature of 50 degrees Celsius, this material begins to soften and flow, filling the microscopic irregularities of the component it comes into contact with, which provides an interface with minimal thermal contact resistance. This is a thin C thermally conductive cap from T-Global Technology. These caps provide electrical insulation of the components, ensuring maximum protection against electrical breakdown while reducing total thermal resistance to the cooling element, heatsink, or chassis. Bergquist offers their dispensable, self-curing, two-part gap filler. These thermally conductive liquids are specifically designed for excellent thermal and mechanical performance. For heat sinks, I have this rather small aluminum anodized heatsink from Assman WSW Components. I also have this aluminum 2.5 watt low profile heatsink for TO 220 parts from Avid. Here I have a couple of parts from Wakefield Vet OmniClip series. This is a 3-clip heatsink for TO 220 devices. And this is a universal heatsink clip. This is a ceramic heatsink also with a clip. This heatsink is also from Advanced Thermal Solutions. It's an aluminum top-mounted push-pin heatsink. This is a fan-ready heatsink from Advanced Thermal Solutions. It's from their FanSync series with maxi-grip attachment and includes the mounting hardware. Here I have two heat pipes. This one is round, measuring 5 by 70 millimeters and is rated at 116 watts. This one is flat and measures 3 by 8 by 250 millimeters, and it has a rating of 50 watts. As you can see, it's bendable. And to wrap up this demonstration, we'll take a look at various fans. This is a popular sized axial fan. It measures 40 by 40 by 20 millimeters. This fan is a bit larger, with dimensions of 120 by 120 by 25 millimeters. It also features a speed sensor, and that's what the third wire is used for. This is a backward curved impeller, also called a centrifugal fan. Air comes in here and gets thrown out at 90 degrees by the backward curved blades. It has 4 wires: power, ground, tachometer, and control input via PWM. These fans are typically used in housing and building type applications where air needs to be moved down an air duct, or where air needs to be moved through a heat exchanger, or where there's some kind of static resistance. This is an AC axial fan with dimensions of 172 by 172 by 51 millimeters. And there's a label showing a wiring connection diagram. And finally, this is an AC centrifugal blower with a forward curved blade type. Like the impeller, this fan also turns air through 90 degrees. So the air comes in here and gets thrown out here. I hope you enjoyed this video from Digi. Thanks for watching.